Once again, welcome back, colleagues, for another session regarding the security. So today we have an interesting topic to discuss and share. We all know that automotive cybersecurity is kind of becoming more and more important in the automotive industry with many complicated features coming in. So today we will be looking into what this automotive cybersecurity is all about in terms of implementation, how it is layered, what is a better approach in the automotive cybersecurity. So here we'll be discussing a bit about the architectural details, and also we will look into one of the or maybe some of the cybersecurity concepts that you can implement in the software level and prevent some major attacks. So this is what we will be mainly focusing today. So to quickly share some thoughts, maybe if we can quickly share the screen. Next slide. Yes. Next. So today we'll be looking into the automotive cybersecurity mechanisms. So initially, to start off with, we will look into the layered automotive cybersecurity approach that is there in the automotive industry. Um, Riva will explain a bit more in detail about what this layered automotive cybersecurity approach is. Over to you, Riva.
Okay. So, as we know that in today's world, interconnected world, the cars are more than just vehicles. They are the rolling computers on the wheels. With rise of advanced technologies such as autonomous driving and connected features, ensuring the security of the vehicle has become the most important thing. So, this is where the layered automotive security approach comes into picture. Let us take an example to understand this approach. So, suppose you have a box of gold that you want to store in your house. So, for as it is the most important thing, you'll have to create some of the security, or you'll have to safeguard it from the thieves to collect it. So, the outermost layer, that is the secure external communication, is something which is similar. Imagine you in your house, you have a tall, strong fence around it, and the fence has a gate. That gate just let the trusted people to come inside and outside. You also have some security cameras and guards, those who checks if the proper people or the trusted people are coming inside and going outside. So similarly, the secure external communication, in terms of the in the context of a car, it is the first layer of the security that protects the communication between your car and the outside world. Firewalls and intrusion detection systems acts as the gate and guards. These are the second layer, which is the secure gateways. These are the part of the second layer, ensuring that only the commands or the data that goes inside and outside the car network are secure. The next layer, that is, as you move inside the house, you'll get to know that there are several rooms inside the house with proper lock. And as soon as you go inside the house, you'll be able to see that there are several rooms, and inside the room, each of the room has a secure lock. Only family members with the proper correct passwords and passcodes are able to enter this room. This ensures that even if someone get passed out from the outer fence, they'll still cannot move freely inside the house without having an authorization. Similarly, within a car, this layer is the third layer, which is the secure in vehicle. Similarly, within a car, this layer secures the communication between different components. For example, engine communicating with the infotainment system and etc. Encryption and authentication ensure that only authorized parts can communicate with each other, keeping unauthorized devices and messages and commands from causing harm. Now, next comes the third layer, which is the utmost important, that is the secure ECU, which is the gold box itself. It is as you can imagine that in your home you have stored that gold box in a particular safe, which have some of the digital systems such as biometric or alarm, which goes off when someone try to temper or touch or change anything with it. Similarly, there is in a car the ECU are like the gold box in the safe. They control the crucial functions like engines and braking system. Secure booting ensures that ECU runs only authentic and untampered software and hardware modules, which acts like the alarm and biometric locks, protecting the integrity and functionality of these critical systems.
Fantastic. Thank you, Riva, for that explanation. So, to quickly summarize, what we understand from the layered automotive security approach is that it's not just one ECU with one layer of security or one security mechanism that is implemented, but it is a multiple layer of things, because the more complex you make it, the more security layers you add, the more complex it becomes for any of the attacker to try to get in. The way Riva gave the analogy of getting breaking into the house and getting the jewel box. So there are multiple layers, and each of these layers will have different kinds of security mechanisms that we can implement. So normally in our previous videos we have talked about Tara security concepts, right, where we are trying to analyze what security vulnerabilities are there, how do we mitigate these security vulnerabilities, and what security mechanisms we will have to implement, which comes as the derivation of these cyber security goals or cyber security requirements. So this is where each of these cybersecurity mechanisms will can be mapped in one of these security layers, which then will help us to secure the complete ECU, thereby securing the complete vehicle. Now, today what we are also going to do is we'll remember this secured approach, the layered security approach, and then we will always come back to this approach. But let's start with one of the security mechanism, a pretty much famous security mechanism which is there. If you are an automotive software developer who's using extensively the AutoSAR OS, be it classic or adaptive AutoSAR, so this is one of the classic security mechanisms or the components that is available in the industry, which is called as SecOC. SecOC stands for Secure Onboard Communication. Now, Dharmesh is going to in detail explain a bit about what secure SecOC is and how it works. Over to you, Dharmesh.
Yeah, thanks, Falcon, for the explanation. Then now we jump into the first security measure, which called the SecOC, which is Secure Onboard Communication. So in automotive security, controls are nothing but the automotive security features that prevents the hackers from intruding into our system. The security controls are brought into the concept that we control the unethical access of hackers into our system. So this terminology came from the ISO 21434, where we called security features uh, to the automotive security controls. Today we will discuss the SecOC, message transmission into the vehicle bus, and also gives the detail about which modules SecOC will interacting uh, other than the one or two modules which is available in the AutoSAR architecture. So if we see here in this image, on the left hand side corner, we have SWC1, which is the software component at the application layer, which uh, holds the signals, and these signals will be transmitted to the COM module. So as we know, COM module is responsible to packing and unpacking of these signals and convert these signals into the PDO for the further communication. Then this COM module will send this PDU to the PDUR. So PDUR module will have the destination addresses and source addresses, which will then route this message to the different modules, underlying layer or the parallel layers. So here, if we see the PDUR, if the message is security relevant, then it will transmit to the SecOC module. If it is normal message, then it will directly transmit to the corresponding bus interface. Now, this how we decide whether the message is security relevant or not. So this all depends on the architecture person. So at the beginning itself, when we design the architecture person will give us the list of the messages that this needs to be secured, and those messages then will be configured as a secured PDU or secure messages. So it's depend on the architecture person who will give us the messages, and that will be secured. So if we identify at the PDUR level whether the message needs to be secured or not, it will then route to the SecOC module. Here you can also see some of the interfaces which SecOC can take place. One is the crypto stack itself, so which is responsible for all the cryptographic operations. So here we have CSM and crypto interfaces. So remember that CSM also required some of the inputs to perform the cryptographic operations. So that's where some of the data it will fetch from the SecOC module. SecOC module, again you can see it upper layer. It will take help of the FVM and key manager to get some input, because SecOC is not alone is capable of doing the all the functionality which will be required for the authentication of the PDU message. So the freshness value, and there is something called key which is required to perform the authentication on the authenticate PDU. So for that reason, there is a application security extension needed, which is holding the submodules, which is the freshness value manager and the key manager. And the key value and freshness value will be taken from this module by the SOC, and then the authentication will be calculated. And then once this message will be secured by the SecOC module, it will route back to PDUR. Then PDUR responsibility to transmit this message to the lower level interface. So here it's a bus interface, means it could be anything, CAN or Ethernet message. Uh, Based on that, Ethernet interface or CAN interface will then transmit to the lower level drivers. And then at the receiver side, the same process will follow. So message will be received at the bus interface level. Then the PDUR level will identify whether the message was the secured one. Then to uh, verify it whether the message is the authentic one, again this message sent to SecOC module, which will then verify the message is authentic. uh, if it is authentic message, then it will route back to PDUR, and PDUR will then move it further to the COM module, where again the message will be unpacked, and then it will transmit to the application. If we identify that message is not authentic, or who is the sender is not the authentic sender, then this message or PDU will be dropped. So this is the total flow. So if in summary I have to say, so what would be the transmit part? So we get the data from the SWC1, then goes to COM when then route to the PDUR to SecOC, and on the SecOC to PDUR again back, then bus interface and automotive bus. At the receiving side, reverse case. So from automotive bus interface will receive this data, then PDUR to the SecOC, and SecOC to PDUR, COM and SWC. Very interesting thing to notice here is here PDUR lies the same level at the SecOC. So it means that whichever the authenticity applies here will be on the message or PDU level, not at the signal level. So that is the one thing to remember. So this is the overall working of the SecOC module. So if you have any questions, yeah, you can ask.
So I have a question here.
Hmm.
So, in what specific cybersecurity threats or attack scenarios does SecOC provide protection or mitigations? And how does its implementation contribute to enhancing the overall security posture of automotive system?
Okay, that's the good question. So to answer to this particular question, So as I mentioned, the SecOC module itself is mainly designed for authenticity, integrity of the message, and replay attack. So it will not do the cryptographic algorithm. So the message will be not encrypted form. So that aspect of the security will not covered by the SecOC module, but mainly it is checking the authenticity of the message, whether the sender is the correct sender or not, uh, and the message integrity means in between nobody who tampered the message, so that will be checked. And it will also check the replay attack. So sometimes we see that the same message is transmitted multiple time and bus will be busy. So in this scenario, to avoid this particular scenario, we can use SecOC. So using the freshness value we will discuss in the further session, will be utilized to avoid this replay attack. But yeah, it will not cover the cryptographic. So if somebody in between the line able to trap this message, then they can read the content because it is not a crypted message.
So, Dharmesh, I have a follow-up question here. So, is this Mac generation a crypto-based generation or not?
Okay, to understand this question better, let's jump into the message formation, uh, which SecOC does, and then we will be clear like how this MAC is generated and whether it requires the cryptographic or not, or both option is possible. So I will jump into the next slide, which is SecOC message format. So now we see about the SecOC format. Basically, what is additional data that SecOC will add within the authentic PDU or message. So in this data, what we received from the upper layer, apart from that, SecOC module will add the freshness value and the MAC, which is message authentication code. We will shortly see how this is generated also and how many types are there. So this whole package then will become our secure IPDU, which will be secured using this MAC address and the original IPDU, and that will be transmitted to the PDUR. So if we see the authentic IPDU is nothing but AutoSAR IPDU that requires protection against the unauthorized manipulation and replay attack. So here we have to see that if any unauthorized people will hack this particular message, then they can try to change this message and again send it. So we have to prevent this. So using the SecOC, this will be ensured that we will come to know if any manipulation happen within this message, because the MAC calculation, whatever happens within here, will not known to the attacker. And the replay attack, as we explained earlier, that will be handled using the freshness value. So freshness value also we have two types, we will discuss further, so which will be then responsible to avoid or mitigate this replay attack. So secure IPDU is the AutoSAR IPDU that is protected by the SecOC protection. The payload of the secure module consists of the authentic IPDU and authenticator. So here MAC also called as authenticator or authenticator because it will authentic this PDU and will provide the protection. The payload of the secure IPDU may optionally include the freshness value used to create the authenticator, or this freshness value I say is optional because when we calculate this MAC, anyway, the calculation will require the counter, monotonic counter, which is nothing but to act as a freshness value. That's why we consider this as a optional. However, it would be better if we add this freshness value. The length of the authentic IPDU or freshness value and authenticator within this secure IPDU may vary from the unique identifiable secured IPDU. So every IPDU here the length of this total message will be vary based on the which type of message we are sending. So it's not constant. It may vary depend on the message length. So there are two types of MAC. One is the CMAC and another is HMAC. So CMAC stands for cipher-based message authentication code, and HMAC stands for message authentication code. By implementing the freshness value, we mitigate the replay attack, and it can be implemented using the counter mechanism and timestamps. So now regarding your question, whether this CMAC or MAC we generate here, which will have the cryptographic involved or not, or it can be having the cryptography algorithm. So I would say answer is both. You can have or use the cryptographic module to provide this MAC and directly append it. So that will be one option. Another option is software based. So in general, here in SecOC, when I refer, it's mostly the CMAC, where we will have a software which have the algorithm. So in previous slide, we seen that we required external support to get the key. So using that key, we have the logic to write the MAC or generate the MAC and also add the counter value. So this will become again the message authentication code. And the other ways, yeah, you can use the cryptographic module if it is configured to directly get the calculated MAC and append it to the PDU. I hope this is clear.
Yeah. So to quickly summarize, the secure onboard communication message format, normally what it contains is it has its own message, whatever you want to communicate, that is there. To that, you will append freshness value. To that, you will also append the MAC. MAC here means the message authentication code. How this MAC is generated? To generate MAC, we use three things: the message itself, the freshness value, and the secret key. So three of these things will go as an input to the MAC. Output is the encrypted string. Now, as Dharmesh mentioned, there are cipher-based MACs or hash-based MAC. Now, when do you use what? It is left to the decision of the architect. The software architect decides based on what system they are trying to, what software they are trying to implement, and what kind of hardware support they have. Based on that, they will come up whether they have to use the cipher based or the hash based. Now, this would be about the Mac.
Yeah, anyone have any other questions?
As we now talked about the freshness value, so I wanted to know a bit
Hmm.
about why do we need the freshness value?
Okay, yeah, that's the good question. So first, let's take an example uh, that you have the now secured message, uh, and in a real-time scenario, if this message is also somehow got to the hacker, and hacker is trying to replicate the same message and simply send it to the destination issue. Now, what will happen is if you have this message which you are trying to send to the destination issue, so bus will take only one, or let's say the configurable message at a one time. So it cannot be like always how many messages you send and all will be transmitted at once. So it is really important that priority wise message will go, and one by one it will be transmitted, and every message will get chance to be transmitted. So at any time bus is busy, then you cannot transmit the message. So in this case, let's say same message is transmitted multiple time. What will happen is bus will become busy, and if very important message needs to be transmitted, that message will not get chance to be transmitted. So in that case, it is required to have some mechanism which we can identify, okay, this message already received, and again it will receive, it will just ignore. this message so that other message will get chance to be transmitted. So that's why we required the uh, freshness value here. So freshness value again will be uh, created using the two mechanism. One is the counter based mechanism where you will have simply mathematical counters to the message in ascending or descending order. Other one is the timestamp. So let's say you configure the counter based mechanism, which means that when you transmit this particular one message, you add a counter value, suppose 10, then the other side at the receiver end, it will check the last message, what it received. It is greater than whatever the message you received, the counter is greater than that. So let's say 1 greater than 10 it should have, then only it will accept. If again the 9 will come, then it will reject. Similarly, there is a timestamp based mechanism uh, using which you generate the freshness value. So this will be based on the timestamp. Here, important thing is when you use this timestamp, the clock which you use to generate this timestamp will be the same at the transmission side as well as the receiver side. Then only both will have the synchronized timestamp generated and it will be verifiable. So yeah, this is the use of the freshness value, and this is how it is generated. Thank you.
Um, so Damish, I have a question. So what key factors and considerations should we take into account when deciding whether to implement SecOC in automotive systems? And how does these factors influence the overall security and performance of the system?
Okay, so that's the interesting question. So to answer that question, I'll just go back to the layered architecture and here to indicate that where the SecOC will fit. So let's say the SecOC will fit mostly in the secured in-vehicle communication. So if you are implementing the solution, then the cybersecurity control will be chosen based on which layer you want to protect. Uh, we are protecting using the SecOC at the second layer because you want to secure the communication within the vehicle, within the issue to issue. So that's where you will choose. What SecOC will be best suit for is, as I earlier mentioned, it's the integrity and authenticity of the message will be protected using this SecOC module. But also we've seen that why it is not mainly doing the cryptographic algorithm, because for that we have separate mechanism and the calculation to apply for the cryptographic or message to be crypted, it is used, and it will also require so much of memory. So for that we have CSM and crypto stack separately. But for SecOC mainly, if you want to check the integrity and authenticity of the message, then you can use the SecOC module.
Fantastic. Just to add on to that, the other factors, maybe in terms of the hardware or where you would use SecOC, would be whenever you are trying to implement secure or say secure onboard communication. Of course, the decision would be coming as part of the threat analysis and risk assessment, the cybersecurity analysis that you would do. But once you choose this, things to be kept in mind would be one, if you are using hardware crypto module, HSM or CSM, software crypto module. So if you are using HSM, then you need to have a separate hardware, etc. There will be computational power. All those things should be kept in mind. Second point that needs to be considered when we are talking about SecOC is with a normal message, there is, let's say, n number of bytes of data that is getting on the bus. The secure onboard communication adds two more, which is the freshness value and the MAC. The size, of course, can vary. The size of the MAC and size of the freshness value can always vary. That means if you are using a CAN protocol, that you have 8 bytes of data that is getting transmitted, then the overall transmission of one particular message will get increased. If it is can empty, then again that would get broken down into multiple messages and then sent. So this is something that needs to be considered, which means based on the communication protocol, you would decide whether how much would be the length of your freshness value, how much would be the length of your MAC, depending on which you would choose the algorithm. Would you use 128-bit encryption algorithm, 192-bit encryption algorithm, 256-bit encryption algorithm? Depends. So these are some of the other things that you would consider. Then the third most important thing, as Dharmesh mentioned, we need to consider is the way we generate the freshness value. It can be a timestamp, which is going to change every other time, or it can be a counter based. Now, why this timestamp or the counter based mechanism becomes important, or why the freshness value becomes important, is whenever there is a replay attack, of course, as Dharmesh mentioned here, you can get the content of the message with SecOC implemented. That means the message itself is not encrypted. It only talks about integrity and authenticity. Now, how does the integrity get evaluated based on this freshness value? So, just to make sure that the same data does not get repeated. So let's give a example of how replay attack would work, because replay attack is something that SecOC prevents, right? So there is the dashboard ECU where you display the speed, and there is the speed, the engine issue, which will give you the engine RPM. Every time you press the accelerator, you get the extra, the current speed. Now let's say there is a communication going on. So you are going at 40 kilometers per hour, then you change to 50 kilometers per hour. The display displays, you are at 50 kilometers per hour. Now let's say there is an attacker. Okay, we will talk about how this attacker got introduced in this scenario in maybe in another session. But let's say there is an attacker already. He or she is able to hear all the messages. That means what the speed ECU is sending to the dashboard ECU. So every time it sends 41, 42, 43, 50, etc. The attacker is also able to catch that information. Now, immediately after it reaches 50, of course, the driver is speeding up. What the attacker does is the attacker keeps sending only 50. So even if we increase the speed 60, 70, 80, the dashboard, let's say, based on the replay attack, what it will receive is it will just keep receiving the 50 kilometers per hour. Even if you are going at a higher speed, you would still see the same value. So this is called as a replay attack. Now what SecOC does is at this point of time using a freshness value, that means it says I will use every time when I send this message, I will use one value, a unique value. And this unique value will keep changing. And how does it change? It will monotonically increase. So this is where monotonic counter comes into picture. Now, what does this monotonic counter mean? It would just increase. So based on this, the attacker will not be able to find out what freshness value needs to be put. So this is where one of the key factors is in a typical, let's say, environment, what you would do is to calculate a freshness value, you would use a trip counter, a message counter, a reset flag. So some of these counters you would use, you would put them together. They based on this, the freshness value will be generated. Now, the fourth important factor is if you had observed, Mac itself has the message, the freshness value, and a secret key. Now, this secret key becomes also a critical factor while choosing the SecOC. How are you managing the secret key? Are you locally storing the secret key? What happens when a new ECU gets introduced in the complete vehicle system? How the secret key is distributed to that ECU? So this is where key management of this secret key itself is also one of the important thing. So to quickly summarize, SecOC itself, whenever we implement, the other factors that we need to consider is should we use HSM or not, or CSM, how the key management will happen, what algorithm would you use to generate the freshness value. These are some of the key things that you would have to look into.
So, since we talked a bit about the SecOC, there are positive points to it, but there would be some limitations. So, what would be the limitations of SecOC?
Good question. So one of the biggest limitation that I would see, as Damesh mentioned, is the message itself is not encrypted. That means if you are sending a sensitive information, of course the message is authenticated and validity is checked, but the message itself, the content of the message itself is known. So if you are broadcasting this message, then this message is available for the attacker to look into. So this is point number one. Point number two, what SecOC cannot prevent is, as we mentioned about the message, that message authenticate, or rather the content of the message itself, uh, denial of service attack is something that cannot be prevented by SecOC. Now, what exactly is this denial of service attack? So let's say we are trying to replay the messages. So replay attack is protected by SecOC. But what happens is if you are flooding the bus with a lot of messages, the receiver doesn't have any other mechanism other than to accept these messages, keep discarding these messages, but we are flooding it. By doing so, what the receiver understands is that the transmitter itself is hacked. That means it is compromised. So any message coming from the transmitter will not be, let's say, validated, will not be accepted by the receiver, thereby denying the complete service of the transmitter. So this is something that the SecOC does not actually authenticate or rather protect. So the third one is RCE. What does RCE stands for? RCE stands for remote code execution. So let's say there is a way where an attacker puts in a remote code onto the memory device, right? And start executing it. SecOC will not be able to detect or prevent the remote code execution. So this is something that SecOC cannot prevent. So these are some of the limitations that the SecOC has. So to quickly summarize, guys, so this was all about SecOC. So we talked about secure onboard communication. What are the mechanisms or what are the factors that we need in order to choose this particular security mechanism? Where does this come from? uh, and what will it protect, what will it not protect. So in future, we also talked about the layered security architecture. So this was one of the security mechanism, and this mechanism is mainly available in the let's say the second innermost layer, that is after the secure ECU. The next one is secure in vehicle communication. So this is inside the vehicle. So secure in vehicle communication. Now do please subscribe to our channel and follow us to get more security mechanisms and to find out where each of these security mechanisms fit in these layered security architecture in the automotive industry. Thank you for watching and have a nice day.